I would like to demonstrate red, green, and blue additive color mixing using a green, red, and blue LED flashlight. When we see red and green at the same time, our brain processes the combination of red and green and we perceive yellow. When we see red and blue at the same time, our brain processes that and we see magenta, blue, and green, and the perception is cyan. And when we see all three at the same time, red, green, and blue, we perceive white. And we can mix various proportions of red, green, and blue and perceive millions of different colors. In class, I showed this daguerreotype of James Clerk Maxwell when he was 24. And this is the earliest image I'm aware of Clerk Maxwell. And what's interesting is what he's holding in his hand here. This is his color top. One of the things he investigated early in his career was color vision. In the early 1800s, Thomas Young postulated the human eye had 3 color receptors and the brain combines the signals to perceive a particular color. He was probably inspired by how painters could use red, yellow, and blue pigments and by properly mixing them produce any color. Young was never able to figure out how to prove his hypotheses. About 50 years later, James Forbes had an idea on how to prove Young's hypotheses. He had a spinning disc and he could put varying proportions of red, yellow, and blue on it, and his thought was then when he spun it, the colors would combine just as they do when painters mix pigments. But he got some puzzling results. When he mixed blue and yellow instead of green as painters do, he got a dull pink. Also, no matter what combination Forbes tried, he could not produce white. Forbes' error was that in the light reaching the eye from his spinning disc, those colors were actually being added together. Whereas when you mix pigments, what you're actually doing is subtracting colors from the light. Clerk Maxwell began his studies of color vision in 1849. He also worked with color tops, and he wondered if Forbes' problem was his choice of primary colors. So Clerk Maxwell tried red, green, and blue and got spectacular results, which he presented to the Royal Society of Edinburgh in 1855. So here I've constructed a spinning top where I can vary the proportions of the various colors. So if I were to turn it like this, where it's just half red and half green, if I would spin this rapidly, we would see the color yellow. And if I did equal proportions of red, green, and blue, and then spun it, what we would perceive is white. With the disc equal parts blue and red, when it is spun rapidly, we'll see magenta. With the disc equal parts green and blue, when I spin it rapidly, we'll see cyan. And with equal parts red, green, and blue, spinning the disc rapidly gives the appearance of white. The typical human eye has 3 different types of cones, and shown here is the response as a function of wavelength of light of the 3 different cones. Now this one shown here is sometimes referred to as the red cone, although its peak sensitivity is at 575 nanometers, which is in the orange range, whereas red light is at around 650 nanometers. This one right here is sometimes referred to as the green cones, and its peak response is at 535 nanometers, which is close to the 510 nanometers of green light. And this one on the left is the blue cone, peak response at 445 nanometers, and the wavelength of blue light is about 475 nanometers. So even though we say these are the blue, green, and red cones, it doesn't really correspond to a particular color, both because they are broad in their response to wavelengths and their peaks aren't at the particular colors. So maybe a better designation is the one where we call them L cones, M cones, and S cones. The S, M, and L refer to short, medium, and long wavelengths. Of the colored cones in the eye, 63% of them are L cones, 31% are M cones, and 6% are S cones. So a population-weighted response of the eye would look like this. So the human eye is most sensitive to light around green because you have a high response from both the M and L cones at the wavelength of green light. Additive color mixing is the process that occurs when you look at a television or a computer screen. Each pixel consists of a source of red, blue, and green light that can be varied in intensity. The result is you can perceive millions of different colors. So specifically, if you're combining equal amounts of red and blue from the pixel, you will see magenta. If each pixel is generating just equal proportions of green and red, you perceive yellow. And if it's blue and green, you perceive cyan. And equal proportions of red, green, and blue result in white. So red and green is yellow, red and blue is magenta, blue and green is cyan, and all three together gives us white. I now want to talk about the process of subtractive color mixing. Subtractive color mixing is the process that occurs when an artist mixes pigments and puts them on a canvas, or when you print something on your color printer. Historically, artists have used red, yellow, and blue as their primary colors. But when you've gone to buy cartridges for your color printer, you found that what is used is magenta, yellow, and cyan. And those choices come about by looking at additive color mixing, and that the combination of red and blue gives you magenta, green and red gives you yellow, and blue and green gives you cyan. When you shine red, green, and blue light on a sheet of paper, the paper will appear white. When you print something on that paper, the pigment is going to absorb some of the light, so not all the red, green, and blue will be reflected. So for instance, if you print something in magenta, we know that magenta results when you see red and blue. So the magenta will allow red and blue to be reflected and absorbs the green. Similarly, if you print something that is yellow, we know you see yellow when you see green and red. So the yellow will allow the green and red to be reflected and absorbs the blue. And when you print something that is cyan, you know we see cyan when we see blue and green. So the cyan will allow the blue and green to be reflected, absorbing the red. So if you wanted to print something red, you would mix equal amounts of magenta and yellow, because the magenta would absorb the green light, the yellow would absorb the blue light, and then the red light would be reflected. Similarly, to print green, you would mix equal proportions of yellow and cyan ink. The yellow absorbing the blue, the cyan absorbing the red, and thus allowing the green to be reflected. And to print blue, you would mix magenta and cyan, the magenta absorbing the green, the cyan absorbing the red, and allowing the blue to be reflected. And other colors can be obtained by mixing appropriate proportions of the magenta, yellow, and cyan ink. And to print something that's dark or black would mean equal proportions of magenta, yellow, and cyan, and enough of it that it absorbs all the green, blue, and red.